Hello friends, welcome to Truth of Physics. This video will be very much conceptual and very much interesting for all of you who are interested in quantum mechanics. Here I will discuss why quantum mechanical states are described by abstract complex vector space. Okay. Now, previously to understand in this video, you must have a knowledge of the sequential Stern-Gerlach experiment and the analogy of the Stern-Gerlach experiment with polarization. So previously I have made two videos dedicatedly on these topics. You can watch those videos. I will give the link of those videos or the playlist of quantum mechanics in the description box. So what is in Stern-Gerlach experiment, we discuss the spin state of silver atoms, right? Now we want to study the spin states, why the spin states behave strangely in the sequential Stern-Gerlach experiment. Like here you can see that SZ component, SZ minus component of the beam is blocked, but after the measurement of SGX component, and then again when we measure the SGZ component, we again get back our SGZ component, but here we have blocked it, but we are again getting this. Now why this is happening, I have discussed it physically with the help of with the analogy of polarization vector, right? This there I have discussed that these spin states or the beams coming out of the SG components, SG compartments like SGX or SGZ, these beams actually behave like the polarization vector. The light, polarized light, means the electric field vector of polarization. It behaves like vector, right? But not exactly like that vector, right? Because you can understand that the spin state is not a real vector like our xy coordinate system vector, any positions vector. It is not like that vector, but its behavior is like a vector, is completely similar like a vector. So that's why it is a general vector, and we call this vector as a abstract vector. And we by these analogies, you can understand when you go through the two videos, we can express the spin states like this. Here you can see the spin states. These are spin states. Okay, this is spin positive and this is negative. Okay, Sx plus and Sx minus states of that beam. Okay, the beam, the silver atom beams going through the SG compartments, SGX cap, these things. So the beams, the state of the beams, we know that the state of the beams can be expressed. This symbol is known as the Kate symbol. Okay, Dirac's notation, Kate symbol. Now by this symbol, by this, if you know this thing, if you know this quantum mechanical state, you can know every possible characteristics of the beam. You can know every details of the beam. So this is known the Kate. Okay, Kate vector. Now this is the need of abstract vector space. Okay, now this can be thought of a linear combination of the SG plus and SG minus, what I have discussed in the previous videos, like here, like the polarization vector, which can be composed, which can be thought the X component, this vector, electric field vector, can be composed of the two components, or the linear combination, from the linear combination of Y component and X component, right? The linear component of Y and X, like this expression. X component vibration can be composed of X component and Y component, and a linear combination with some factors 1 by root 2, these things. So similarly the SGX beam means this state can be composed or can be thought of a superposition of two SG plus and SG minus states, and the superposition equation is like this. So this is the need of abstract vector space. Now what is the need of complex Now you may understand clearly that why there is an z minus component after the blockage of in the second part, right, in the sequential standard experiment third part, like here, why after the blockage of this thing, we get the things again, we get the sz minus beam again after the third measurement. That is because sz component, when passed through this, becomes sx plus beam, and then immediately when you get sx plus and sx minus beam, sx plus and sx minus beam is nothing but the linear combination of like the linear combination of sc plus and sc minus beam, right, like the equation here is, this is the linear combination of these two things. And that's why after that, when we want to, or when we pass the beam through z component, we get these two components, obviously, because this is made up of these two things. Now let us understand what will be the state this sy plus and sy minus, these states, what will be this? Can this also be represented or be expressed as a linear combination like the same thing, like is z plus 1 by root 2 is z minus? Can this be written like this? Why I'm writing like this? Because you may understand that, just remember these things, okay, remember the indices. Now these beams SG plus are going in y direction and fall on or pass through the SGX compartment and giving rise to SX plus component. This can be thought of, or the same thing you can think, and giving rise these things, these results what we have discussed, and you can think that the same thing can happen when this SZ plus beam will go in the x direction, okay, and another case in the x direction and pass through SGY compartment, SGY, okay, SGY means the magnetic field is in the y direction, and giving rise of SY plus and minus. Then you can think that these two things that this beam is going in the y direction and giving rise to xx plus, and the beam going in the x direction and giving rise to the sy components, these two things are similar, just same. And from that analogy I have written this thing. But here you can see that then what is the difference between sy and this sx? We cannot distinguish between these two things, sy or sx. We cannot distinguish between these two things because these two things are just same. So to distinguish between these two things, there should be some another thing, right? There, this should not be exactly the linear combination. There should be some different linear combination of these things. So that I will discuss right now. To understand this thing, we can think of the analogy of, again, the polarization of light, and this time the analogy of circularly polarized light. Circularly polarized light. And the equation of circularly polarized light is like this thing, right? The same thing, but there is an additional phase difference. That is the y component is this is for the case of right circularly polarized, okay, right circularly polarized light. You can check out the video of polarization that I have discussed in another video, the polarization of light, to understand these things. Now this is the right circularly polarized light. There should be a pi by 2 phase difference between the y component light and the x component, okay. So this relation represents a circularly polarized light. Now you can understand that how this thing will do our job of this problem. Now this can be written, if we write this in complex notation, then we can write like this is 1 by root 2 x cap, this thing x cap and e to the power I kz minus omega t, right? Means we are taking the real part, cos of this thing, cos of kz minus omega t, plus just take out this thing, means e to the power I pi by 2, okay, and 1 by root 2, and uh, e to the power I kz minus omega t. Now you can think that if you plug this into this, then it will, there will be a plus pi by 2, and that will resemble to this thing, right? This thing. So we are taking out the e to the power I pi by 2. Now e to the power I pi by 2 is nothing but only I, right? So this will become x cap e to the power I kz minus omega t plus 1 by root 2, or simply I over root 2 iota e to the power I kz minus omega t, this thing. So this is the expression of circularly polarized right, the electric field of the circularly polarized right. Now if you think, or if you make the analogy of the Sy plus atoms, or Sy plus state, spin state of that silver atom with the right circularly polarized light, and Sy negative with the left circularly polarized. For left circularly polarized you have to do only minus sign here. So you can understand that these things is what, these things are, just by analogy you can understand that these things are the Sz, right? Sz components. So this is Az plus, this is Az minus, right? So plus and minus, this minus is this minus is for left circularly polarized. Now I over root 2, and this is the analogy of it is Z negative, this state gate, and this is equals to 1 over root 2, this is equals to the Sy, right? Sy plus and minus both, plus minus. So you can understand from here that the Sy, if you make the analogy of circularly polarized light here, then all the things are fit properly, right? Like Sy component or Sy spin state of the silver atom can be thought of a superposition of the Az plus and Az minus, and here is no difficulty to differentiate between the Sy and our previously stated Sx, like this, because there is no I here and here is a I. So here you can see that there is an I term, means this is no longer a real quantity, this now becomes a complex. So this is a vector obviously, and this is a complex, and this is not a real vector or a normal vector, right? Normal xy vector, position vector. This is the abstract, more general sense of vector, abstract vector, and that is why the complex, because iota term comes in the picture. So this is why the reason of the quantum mechanical state, or the idea that the quantum mechanical states are to be represented by vectors, in an abstract complex vector space. So that is all about today's video. I hope that you have understood the concept of coming the abstract complex vector space in picture of quantum mechanics all over the quantum mechanics. So share this video with your friends and take care of yourself. Thanks for watching.